PhD in Control Science Engineering from Harbin Engineering University in China. She's currently a researcher at the École Nationale Supérieure des Technologies Avancées in Algeria. She specializes in the design and control of autonomous special vehicles operating in marine environment. So without losing time, we're gonna welcome you, Dr. Mounia. So please have the floor. Thank you very much. And
Thank
we,
you.
excuse me, we have 60 minutes, which is 1 hour. So we're gonna manage 50 or 55 minutes for your presentation and having around 10 minutes Q&A, so that we can allow people to ask some questions. So please have the floor. Thank you very much.
Thank you very much, Mariama, for this presentation. Good afternoon, everybody. And today I will present for you our research developments in advanced material tailored for enhancing the longevity and sustainability of hydroacoustic station. This is the result of combined efforts made by our multidisciplinary team of researchers. So first, here, as you are surely aware of, the hydroacoustic stations of the CTBTO operate under some of the most extreme and challenging conditions on the planet. These stations are located in a remote, deep sea environment where they endure immense pressure, frigid temperatures, and corrosive salt water. Therefore, sustainment action are crucial for preserving the operability of the CTBTO's hydroacoustic stations. Most importantly, regular maintenance, timely repairs, and technological upgrades to ensure that these stations continue to function effectively, providing accurate and reliable data. So it is only by addressing this area that the CTBTO can maintain the integrity of its global monitoring system, ensuring continued compliance with the comprehensive nuclear test ban treaty and contributing to international security. Of course, these sustainment activities are conducted in relation to the on-land outside plant equipment and the underwater system. So here we address the problem of corrosion. According to our understanding, the corrosion remains the most challenging condition faced by the hydroacoustic stations. Indeed, the accelerated degradation caused by corrosion poses a severe threat to the structural integrity and operational reliability of the stations. The additional materials and protective measures are proving insufficient in this hostile environment, making the development and implementation of advanced coating material imperative. These cutting-edge coatings must be engineered to provide exceptional resistance to corrosion, ensuring the long-term durability of the station. So it is therefore by addressing these challenges that we can secure the continued functionality and effectiveness of these vital components in global nuclear test monitoring. Now, let's talk about the superhydrophobicity and the role of superhydrophobic coatings in addressing the corrosion issues. Superhydrophobic coatings are characterized by their extreme water-repellent properties, offering a promising solution to pervasive corrosion issue in hydroacoustic stations. Typically, these coatings can create a surface that minimizes water contact by causing water to build up and roll off, significantly reducing the likelihood of corrosion-induced moisture accumulation. Indeed, this water-repellent behavior is crucial in marine environment, where constant exposure to salt water accelerates the corrosion of submerged structures. In addition to water resistance, superhydrophobic coatings can also reduce the adhesion of marine organisms, such as barnacles, which contribute to biofouling and further exacerbate this corrosion. So by preventing both water ingress and biofouling, these coatings can enhance the durability of hydroacoustic stations, extending their operational life and reducing maintenance costs. So now, let's discuss the science behind it. What is this superhydrophobicity? Superhydrophobicity is closely related to the water contact angle, which is the WCA. This is defined as the angle where a liquid vapor interface meets a solid surface. According to the WCA value, we can define if a surface is superhydrophobic or not. For instance, in the upper figure here, the surface is superhydrophobic when a WCA is between 150 and 180 degrees. It is hydrophobic if a WCA is between 90 and 150 degrees. And less than 90 degrees, it is hydrophilic or superhydrophilic. Superhydrophobicity was always initially discovered in nature, as we can see here from the SEM image in the bottom left. We can see superhydrophobic surfaces at low and high magnification of a lotus leaf. Here we have a WCA of 162 degrees, which is a superhydrophobic surface. Now, how is this superhydrophobic surface fabricated? Surface chemical composition and surface roughness are the key factors contributing in the formation of superhydrophobic surfaces. There are many methods and techniques to create roughness, followed by modification to achieve superhydrophobic surfaces, such as we have templating, etching, hydrothermal synthesis, anodization, electrodeposition, and most importantly is nanocomposite spray coating. Nanocomposite spray coating offers a cost-effective method for creating superhydrophobic surfaces. By using advanced nanomaterials, this technique achieves high-performance water repellency at a low cost compared to the other methods. It provides an efficient and economical solution for developing durable hydrophobic coatings across various applications. Let's now move on to the specific case study we performed recently. As I stated in the previous slide, here we have previous slide, the nanocomposite spray coating can be seen as the most adequate and cost-effective technique to achieve superhydrophobic coatings. In this case, a new nanocomposite was developed for a high-performance phthalate resin and seal and surface modified titanium oxide nanoparticles. The phthalate resin are considered as one of the most advanced thermosets, featuring an exceptional thermal stability over a wide range of temperature, a very low water uptake, a high cross-linking degree, and most importantly, a low melt viscosity and large processing window, which allow the preparation of nanocomposite through the spray coating technique. Here, the phthalates are synthesized by a simple nucleophilic displacement of a neutral substituent activated by the cyano functions. Multitude of possibilities are available by changing the phenolic precursors in order to tailor the final properties of the polymer. Meanwhile, the use of environmental friendly precursors like eugenol, cardanol, among others, allow the development of biopolymers displaying some of or the same of better performances than their petroleum-based counterparts. Prior to the nanocomposites preparation, a chemical surface modification is applied to the titanium nanoparticles to improve their adhesion and dispersion within the polymer. The sealant surface modification of titanium nanoparticles also enhances surface hydrophobicity by bonding hydrophobic organic chains to the nanoparticle surface. The sealant molecules react with hydroxyl groups on the titanium, forming a hydrophobic layer that repels water. This modification reduces the surface energy of the nanoparticles, leading to decreased wettability and improved resistance to moisture. The result of the FTIR analysis is displayed in this figure, in the right figure. The FTIR was used to explore the effect of the saline coupling agent of the titanium nanoparticles outer surface. The figure shows the spectra of both of the native and treated titanium nanoparticles, and the finding confirmed that the grafting of the sealant agent on the nanoparticles surfaces. Here, nanocomposites were prepared by adding the necessary amount of the treated nanofillers, ranging from 2 to 6% in an increment of 2% into a glass vessel containing a dissolved tannate resin. To assure the much better dispersion of the titanium nanoparticles, the mixture was vigorously stirred using a mechanical agitator and then sonicated. The selected substrate used to assess the corrosion protective properties was carbon steel panel. The deposition of the nanocomposites mixture described above was performed by a spray coating process. The final thickness of all coatings were about 120 micrometers. The scanning electron microscopy was used to study the morphology of the coating. In Figure A, the unfilled resin shows smooth and featureless structural surface morphology. On the other hand, adding the sealant-treated titanium nanoparticles caused an increase in the surface roughness, hackling for all nanoparticles here showed in the figures B, C, and D. The WCA measurement confirmed that all nanocomposites had values over 150 degrees and were all deemed superhydrophobic. The corrosion protective properties of the nanocomposite coating were tested using electromechanical impedance spectrometry, EIS, measurements, which were performed on an potentiostat in a conventional 3-electrode cells. These measurements were taken at different immersion times, were performed over a frequency range of 100 kHz and 10 MHz. The evolution of the impedance modulus of the initial immersion stage for the substrate, the neat resin and its related nanocomposite at 2, 4, and 6% nano titania loadings, it presented in this figure. The findings showed that adding the titania nanoparticles enhanced the corrosion protective properties of these coatings. A gradual increase in the modulus value has been recorded with the increasing of the amount of nanoparticles. These interesting results are mainly attributed to the superhydrophobicity and high cross-linking density, which isolate the substrate from the solution, leading to better anti-corrosion properties. Here we have the evolution of the impedance modulus at low frequencies for all the samples at different immersion times. What can be said for sure is that a prolonged contact with a saline environment for more than 1 year did not significantly alter the protective properties of the nanocomposite. Here, the mechanical resistance was investigated because in deep sea environments, materials are subjected to extreme conditions, including high pressure, corrosive seawater, and potential abrasive interaction with particles or marine life. So a coating with high microhardness is generally more resistant to deformation under pressure, which can be advantageous for maintaining the structural integrity of the material it covers. Different nanocomposites showed a much ameliorated microhardness values as the amount of titanium nanoparticle increased. In fact, the maximum microhardness values reached 500 megapascal, has been recorded at 60% of nanofillers. Also, thermal properties were investigated, where coating materials for deep sea applications must endure extremely low temperatures while maintaining their structural integrity. Thermostability performances assessed by thermogravimetric analysis confirmed that the nanocomposites coatings retain their structural integrity over a wide range of temperature from -50 to 500 degrees Celsius. So here, to conclude, here superhydrophobic coatings create a barrier that significantly reduces water contact, effectively preventing corrosion in the harsh marine environment while hydroacoustic components operate. Talented titanium nanocomposites can be a cost-effective candidate for use within a multi-layered defense strategy against corrosion. The reduced corrosion and maintenance needs translate into long-term cost saving. And to confidently verify the long-term applicability of superhydrophobic coating in hydroacoustic stations, further studies under real marine conditions are necessary, ensuring this solution meet operational demands. So this is it for my presentation. How to...
Okay, thank you very much, Dr. Mounia, for your wonderful presentation. And we would like to thank you very much for this title, because when we see in the different presentation or workshop or conferences, we mainly see subject like data analysis, research on the subject, and so on, things like that. But today you showed us something very interesting, how to maintain the network itself so that it works very sufficiently, and in terms of hydroacoustic network. So I'm gonna open the questions to the audience. If someone has a question to Dr. Mounia, please have the floor and raise your hands, and then you take the floor. And I have a few questions, but I'm gonna wait for the audience to ask questions first, and then I can ask mine. So please, if you have something to say, it's the moment. Okay, Ben, go ahead.
Yeah, thank you. Thank you very much for the talk. I was going to ask about what do you think the implications are here in terms of